Material selection for specific applications based on NORSOK Standard M-001. Ensuring reliable materials for demanding industrial environments. Overview and importance of material selection. Material selection is a critical aspect of engineering design, particularly in oil and gas applications where safety, reliability, and cost-effectiveness are paramount. NORSOK Standard M-001 provides guidelines to ensure that materials used in offshore and subsea environments meet stringent requirements for corrosion resistance, mechanical strength, and durability under extreme conditions. The introduction should emphasize why proper material selection minimizes operational risks, prevents failures, and ensures compliance with international standards. It also addresses environmental factors such as temperature, pressure, and exposure to corrosive substances like seawater and hydrocarbons. Understanding these principles is essential for engineers to design systems that withstand harsh environments while optimizing lifecycle costs. Material requirements for well completion. Well completion involves installing equipment and materials that enable the safe and efficient production of hydrocarbons. Materials must resist high pressures, temperatures, and corrosive fluids. Common choices include corrosion-resistant alloys or CRA such as stainless steels and nickel-based alloys for tubing and casing. Selection criteria include tensile strength, resistance to sulfide stress cracking, and compatibility with completion fluids. NORSOK M-001 emphasizes the need for materials that can handle sour service conditions, where hydrogen sulfide or H2S is present, requiring compliance with ISO 15156 standards. Proper selection ensures long-term integrity and reduces maintenance costs. Material considerations for wellhead systems. Wellhead and Christmas tree equipment operate under extreme conditions, including high pressure and exposure to seawater. Materials must exhibit excellent corrosion resistance and mechanical strength. Carbon steels with corrosion-resistant cladding, duplex stainless steels, and nickel alloys are commonly used. NORSOK M-001 recommends rigorous testing for weldability and fracture toughness. Surface treatments and coatings may also be applied to enhance durability. The choice of material impacts operational safety and reliability, as failure in these components can lead to catastrophic blowouts or environmental hazards. Selection of structural materials for offshore platforms. Structural materials for offshore platforms must withstand dynamic loads, fatigue, and corrosive marine environments. Carbon steel is widely used due to its strength and cost-effectiveness, but it requires protective coatings and cathodic protection to prevent corrosion. High-strength low-alloy steels may be selected for critical load-bearing components. NORSOK standards specify requirements for toughness, weldability, and resistance to brittle fracture at low temperatures. Material selection also considers fabrication processes and inspection requirements to ensure structural integrity throughout the platform's service life. Materials for production and water handling systems. Production systems handle hydrocarbons and produced water, which often contain chlorides, CO2, and H2S, creating a highly corrosive environment. Materials such as duplex stainless steels and nickel alloys are preferred for their resistance to pitting and stress corrosion cracking. For piping and vessels, carbon steel with internal coatings or linings may be used to reduce costs while maintaining corrosion protection. NORSOK M-001 emphasizes compatibility with process fluids and the need for regular inspection and maintenance to prevent failures. Let's review the material selection for different systems and equipment used in production, process, and produced water systems. This table outlines the recommended materials for each category to ensure durability and corrosion resistance. Number 1, wellhead equipment or XMOS trees. For wellhead equipment and XMOS trees, the primary material is low alloy steel with an alloy 625 weld overlay on wetted surfaces. This combination provides excellent resistance to corrosion in harsh environments. Number 2, piping, valves, pumps, and inline instruments. In piping systems, valves, pumps, and inline instruments, we use Type 22 CR duplex stainless steel, Type 25 CR duplex stainless steel, and Type 6 MO stainless steel. These materials are chosen for their strength and ability to withstand aggressive fluids. Number 3. Pressure vessels. For pressure vessels, the options include Type 22CR and 25CR duplex stainless steel, as well as carbon steel with alloy overlays such as alloy 625, alloy 825, or alloy 904. These overlays can be applied as cladding or weld overlays to enhance corrosion resistance. Number 4. Vessel internals. Inside the vessels, we typically use 316 stainless steel, Type 22CR duplex stainless steel, or Type 25CR duplex stainless steel. These materials ensure the internal components remain protected against corrosive fluids. Number 5. Low corrosivity systems, for piping and vessels in low corrosivity environments. CR, corrosion-resistant alloy, or carbon steel is sufficient. This helps optimize cost without compromising performance. Number 6. Flare systems. Moving to flare systems, there are two key components. Relief system, uses Type 6MO stainless steel and Type 25CR duplex stainless steel, especially for temperatures above -46 degrees Celsius. Burner components, made from alloy 800H, alloy 800HT, alloy 625, and 310 stainless steel, suitable for temperatures below 650 degrees Celsius. Material selection for injection systems. Injection systems introduce water, gas, or chemicals into reservoirs to maintain pressure and enhance recovery. These systems often involve aggressive fluids, requiring materials with high corrosion resistance. Duplex and super duplex stainless steels are commonly used for piping and valves. Elastomers and seals must also be compatible with injected chemicals. NORSOK guidelines recommend thorough evaluation of material performance under varying temperatures and pressures to ensure long-term reliability. Let's take a look at Table 3, which outlines the recommended materials for different components in water injection systems. This table is divided into three main sections: aerated seawater, deaerated seawater injection, and produced water and aquifer water injection. Section 1, aerated seawater. For systems handling aerated seawater, the materials need to resist corrosion caused by oxygen-rich environments. For wellhead equipment and XMOS trees, carbon steel with an alloy 625 weld overlay is used on wetted surfaces for enhanced corrosion resistance. Piping, valves, and inline instruments typically use Type 25CR duplex stainless steel, GRP, or titanium. These materials provide strength and corrosion protection. Pumps are made from Type 25CR duplex stainless steel. Please note the associated references. Notes 1, 2, 3, and 4 provide additional design and material considerations. Section 2, deaerated seawater injection. In systems where seawater is deaerated, the corrosion risk is lower, but material selection still matters. Wellhead equipment and XMOS trees use low alloy steel with alloy 625 weld on wetted surfaces. Piping and valves can be FRP or GRP for low-pressure applications, or duplex. Stainless steels like 22CR and 25CR for higher strength. The deaeration tower uses carbon steel with internal organic coating or lining, plus cathodic protection at the bottom section to prevent localized corrosion. Pumps are made from 22CR or 25CR duplex stainless steel. Section 3, produced water and aquifer water injection. For produced water and aquifer water injection systems, the material selection follows the same guidelines as for deaerated seawater. This is summarized in Note 5, Table 3. In summary, material selection depends on the oxygen content and pressure conditions of the water being injected. Duplex stainless steels, carbon steel with protective overlays, and GRP are common choices to ensure durability and corrosion resistance. Material selection for utility systems. Utility systems include cooling water, heating, and air systems, which may expose materials to seawater or treated water. Carbon steel with protective coatings is often used for low-pressure applications, while stainless steel may be required for high-corrosion environments. Material selection considers factors such as temperature, pressure, and fluid composition. NORSOK standards ensure that utility systems maintain operational efficiency and safety throughout their life cycle. Let's take a look at Table 4, Materials for Seawater Systems. Table 4 defines seawater service materials by subsystem. 25 CR duplex is our baseline for pumps, valves, and general piping due to strong pitting/crevice resistance and high strength. Where conditions are more severe, high temperature, oxygenated, or stagnant, titanium or 6MOSS should be used. FRP/GRP and lined carbon steel are cost-effective alternatives but demand strict QA on lining integrity and flange details. In GRP systems, compatible options include FRP/GRP, NIL bronze, titanium, duplex, and lined carbon steel, watch galvanic couples. For inline instruments, we may use alloy 625, C276, or C22 to address crevice-prone small passages. Next steps: confirm environmental envelope per subsystem, finalize welding/inspection clauses, and standardize instrument metallurgies. Let's take a look at Table 5, Materials for Waste Heat Recovery Units or WHRU, Material Selection for Waste Heat Recovery Units under NORSOK M-001 Cold Casing Design, Max External Temperature 200 degrees Celsius, specifies Type 316 stainless steel with thermal spray aluminum or TSA for external shell protection, with no internal coating required. Piping must resist chloride stress corrosion cracking, with options including ASTM A335P11 carbon steel, alloy 625, and fins per ASTM A409, internal casing. Shell use Type 321 stainless steel for high-temperature stability, and heat exchanger tubes shall be ASTM A335P11 for creep and oxidation resistance. All selections require end-user review and approval, and sulfuric acid corrosion risk must be considered in low-temperature zones. Let's take a look at Table 6, Materials for Other Utility Systems. Table 6 outlines the recommended materials for various utility services to ensure durability and corrosion resistance in industrial environments. For piping and vessels handling fresh and potable water, GRP, Type 22 CR duplex stainless steel, and Type 316 stainless steel are preferred, while open and closed drains use Type 25 CR duplex stainless steel and GRP/FRP. Sewage systems require Type 316 stainless steel or duplex grades, and jet fuel lines rely on Type 22 CR duplex stainless steel. Tanks for dry fuel gas and diesel should be carbon steel or Type 316 stainless steel, whereas instrumentation uses marine-grade alloys like 6MO and duplex stainless steel. Firefighting systems employ carbon steel for deluge piping and CRA for AFFF systems. Freshwater, lubrication, hydraulic fluids, and methanol applications primarily use Type 316 stainless steel and duplex grades. For heating and cooling media, carbon steel and CRA are common, while HVAC systems incorporate LDSS, aluminum alloys, and coated carbon steel. Lastly, chemical injection systems demand high-performance materials such as titanium, GRP, and duplex stainless steel to withstand aggressive conditions. Material selection for subsea pipelines and flowline systems. Subsea pipelines transport hydrocarbons under high pressure and temperature, often over long distances. Materials must resist external corrosion from seawater and internal corrosion from transported fluids. Carbon steel with corrosion-resistant coatings and cathodic protection is widely used, while CRA cladding or solid CRA pipes may be required for severe conditions. NORSOK M-001 specifies testing for fracture toughness and weld integrity to ensure pipeline reliability. Material considerations for subsea systems. Subsea production and injection systems operate in deep water environments with high hydrostatic pressure and low temperatures. Materials must provide exceptional corrosion resistance and mechanical strength. Duplex stainless steels, nickel alloys, and titanium are commonly used for critical components. NORSOK standards require rigorous qualification testing, including corrosion and fatigue assessments, to ensure long-term performance under extreme conditions. Let's take a look at Table 7, Materials for Subsea Production and Injection Systems. Table 7 specifies the materials required for subsea production and injection systems to ensure reliability under harsh offshore conditions. For wellhead equipment and XMOS trees, refer to subclause 5.3. Large bore piping should use Type 22CR or 25CR duplex stainless steel, Type 6MO stainless steel, or carbon steel with alloy 625 weld overlay for corrosion protection. Valve bodies and bonnets for large bore applications require similar duplex grades or carbon steel with alloy 625 overlay welding, while valve internals demand high-performance nickel alloys such as 625, 716, 718, 725, 825, and 925 for durability. Small bore piping, tubing, and valves typically utilize Type 316 stainless steel, duplex grades, Type 6MO stainless steel, or alloy 625 for enhanced resistance to seawater and injection fluids. Notes emphasize that corrosion-resistant alloys with PRE greater than 40 are mandatory for raw seawater, and carbon steel may be used for dry gas and deaerated water injection with alloy 625 cladding in seal areas. Material selection for mooring systems for floating units. Mooring systems secure floating units such as FPSOs and drilling rigs. Materials must withstand cyclic loading, seawater corrosion, and mechanical wear. High-strength steel chains and synthetic fiber ropes are commonly used. Protective coatings and cathodic protection are essential to extend service life. NORSOK guidelines emphasize fatigue resistance and inspection protocols to prevent failures that could lead to loss of station keeping capability. Material selection for fasteners. Materials for pressure equipment and structural use. Fasteners used in pressure equipment and structural applications must maintain integrity under high loads and corrosive conditions. Alloy steels with protective coatings are common, while stainless steels or nickel alloys may be required for severe environments. NORSOK M-001 specifies mechanical properties, corrosion resistance, and compatibility with connected materials to prevent galvanic corrosion. Proper selection ensures safety and reliability in critical joints.